Heidi-ho, Renaissanceteers, and welcome to the solution of Renaissance puzzle number 286, intersection of two cylinders. Here is the puzzle. Two cylinders, each 2 inches in diameter, intersect each other at right angles. Their axes are coplanar. What is the volume of intersection? This puzzle was a homework problem in my freshman calculus course many moons ago, and it stuck with me because it was a fun one to solve. You might be tempted at first to think that the intersection of two cylinders forms a sphere, but that is not quite right. Here is another view of the two cylinders intersecting. If you look down this axis, you see a pink circle. And if you look down this axis, you see a blue circle. But if you remove all the cylindrical material outside the volume of intersection, you see a pink and blue square. So I made this model of the intersection of two cylinders out of construction paper to give you a better view of it. So you can think of it as a red cylinder intersecting with a blue cylinder. And in this view, it looks like a red circle. And in this view, it looks like a blue circle. But in this view, it looks like a red and blue square. I tried to draw a 3D picture like this, but was not happy with my own artwork. So I Googled two cylinders intersection image and found lots of them. I also found that the shape has a name. It is called a Steinmetz solid, after mathematician and electrical engineer Charles Steinmetz, who studied this shape and other related shapes. Steinmetz was a pioneer in the development of alternating current that made possible the expansion of the electric power industry. The Chinese have a different name for this solid formed by the intersection of two cylinders. They call it Mo He Fang Gai, which means two square umbrellas. And in fact, if you split it into two pieces, it does in fact look like two square umbrellas. Ni hao, ni shi huan wo de yu san ma? You probably thought I was someone from Beijing or Shanghai with this Mandarin accent and my authentic Chinese costume. But don't be fooled, it's just me, the Grand Fromage. So how do we go about analyzing this shape? Let's look at its top half and think of it as a stack of very thin square slabs, getting smaller and smaller as you get to the top of the stack. Imagine the base of the stack centered on the y-axis of an XYZ coordinate space. The volume of each square slab is the area of the square times its thickness, delta y, and let's use lowercase d to mean delta. Let's examine a single square centered on the y-axis at height y above the xz plane. The distance from the center of the square to its right side is x, and the distance from the center of the sphere to the right side of the square is radius r. Pythagoras tells us that x squared plus y squared is equal to r squared, or x squared is equal to r squared minus y squared. The full width of the square is 2x. So the area of the square is equal to the quantity 2x squared, which equals 4x squared. And plugging in our expression for x squared above, this equals 4 times r squared minus y squared. To find the volume of the top square umbrella, we need to sum up all the volumes of each individual square slab of thickness delta y. Let's use this funny-looking S symbol to mean sum. So the volume of the top square umbrella is equal to the sum of the volumes of each square slab, which is the area of each square, 4r squared minus y squared, times the thickness of the square slab, delta y. And we will do this sum from y equals 0 to y equals radius r. Now those of you who have studied calculus will recognize this notation and know that it is called the integral of the function 4r squared minus y squared with respect to y. For the rest of you, consider this to be a very brief introduction to integral calculus. Integration is the summation of an infinite number of infinitesimally small pieces. This may seem like a daunting task, but Sir Isaac Newton and Gottfried Wilhelm von Leibniz taught us how to do it back in the 17th century. So let's do the math. The integration yields 4r squared y minus 4y cubed over 3, evaluated from y equals 0 to y equals r. This yields 4r cubed minus 4/3 r cubed, which equals 8/3 r cubed. Remember that this volume calculation is just for the top umbrella of our two square umbrellas shape. So the volume of the top and bottom umbrellas together is 16/3 r cubed. Let's do a quick sanity check on our volume calculation. We have determined that the volume of the Steinmetz solid is 16/3 r cubed. For r equals 1 inch, the volume is approximately 5.33 cubic inches. Now let's look at the volume of the sphere of radius r that just fits inside the Steinmetz solid. Its volume is 4/3 pi r cubed. For r equal to 1 inch, its volume is approximately 4.19 cubic inches. And finally, let's look at the volume of a cylinder enclosing the Steinmetz solid. Its volume is its length L times pi times its radius squared. For length equal to 2 inches and radius equal to 1 inch, its volume is approximately 6.28 cubic inches. So as expected, the volume of our Steinmetz solid is larger than the sphere it encloses and smaller than the cylinder that encloses it. This supports the correctness of our solution. Happy Renaissancing!